So long polynomial division is going to be used to divide this polynomial by this binomial. And as the name suggests, we're going to use our long division bar that we so frequently see back in basic math. My 3x plus 2 is my divisor. My dividend is this polynomial here. Now notice I go from a third degree term down to a second degree term. But then I go from a second degree term down to a 0 degree term. That means I'm missing a first degree term in here. And so therefore I must insert what's called a placeholder. Very important to have this placeholder in here. If you don't have this placeholder in here, then things are not going to line up properly and your division is not going to work well. It won't work at all. Okay? So you gotta have that placeholder there. Another observation is make sure your divisor and dividend are written in descending order, where the degree of each term decreases from left to right. All right, so let's begin here. I am going to begin my division. So I ask myself, 3x divides into 6x cubed how many times? This is optional off the side of your paper. You can do this to help you out if you want. You don't have to though. 6x cubed. You can place that over 3x and then reduce this. 6x cubed over 3x reduces down to 2x squared. That becomes the first term in your quotient. In all the algebra books I've ever seen, authors tend to like to line up like terms in columns here when performing this division. So instead of putting the 2x squared over the 6x cubed, I'm going to put it over the 5x squared. Now 2x squared is going to get multiplied by our divisor here. 2x squared times 3x, and that's a 6x cubed. 2x squared multiplied by 2 gives us 4x squared. Now I'm going to subtract off this whole polynomial. Make sure you put this polynomial inside parentheses, otherwise you'll have an error. 6x cubed minus itself gives us 0. Negative 5x squared subtract 4x squared is going to give us what? You got to be careful of your signs here. This is negative 5 subtract 4. So it's going to give us a negative 9x squared. Drop down the next term as we set ourselves up for round 2 of division. So round 2 now for division, we ask ourselves how many times does 3x divide into negative 9x squared? To answer that question, feel free to take the negative 9x squared off the side of your paper, place it over 3x, and reduce this. This reduces down to negative 3x. So that becomes the next term in your quotient. Take the negative 3x, multiply it by your divisor. So negative 3x times 3x is negative 9x squared. Slide it underneath here. Negative 3x times positive 2 is minus 6x. Subtract off the whole polynomial. Negative 9x squared minus itself is 0. 0x subtract the negative 6x. What's 0 subtract negative 6? That's really 0 plus 6. So this would be positive 6x. Drop down to minus 3 for another round of division. Finally, we ask ourselves, how many times does this 3x here divide into 6x? Take the 6x, place it over 3x and reduce this. And the next term in your quotient appears to be positive 2. Take the 2, multiply it by the divisor. 2 times 3x is 6x. 2 multiplied by 2 is plus 4. Subtract off the whole polynomial. 6x minus itself is 0. Negative 3 subtract 4 is negative 7. Notice we have nothing else to bring down, so our division has terminated. And you are looking at the quotient up here. This is your quotient. Normally back in elementary and intermediate algebra, we bring the remainder. This is called your remainder. We bring the remainder up and place it over our divisor and add it to the rest of our quotient here. So now, since that's a negative 7, I'm going to say minus 7 over 3x plus 2. And this is normally what we called the answer back in elementary or intermediate algebra. That is called long polynomial division. It's not a favorite among students, as you can see why. It does have a lot of steps involved in it. But there are moments, ladies and gentlemen, in higher level math and calculus too. There's times when you have to perform long polynomial division when working with rational expressions. So it does have a value. And it is something that you want to touch base with. Now, there is a division algorithm here that is laid out in this section that shows us another way to represent the answer of our long polynomial division problem here. And I'm going to show you what this division algorithm is about. It says basically if you take a polynomial function f of x and divide it by some polynomial d of x, then when you get done doing this division, your polynomial function f of x can be represented this way. It can be represented as your divisor polynomial, which is d of x, times some sort of a quotient polynomial, q of x, plus some sort of a remainder polynomial, r of x. That's another way to represent this. So I could have I could take this if I wanted to represent the answer a different way. And I could say 6x cubed minus 5x squared minus 3. So 6x cubed minus 5x squared minus 3, I could say is equal to my divisor, which is 3x plus 2, times my quotient, which is 2x squared minus 3x plus 2, plus my remainder, which is to say plus a negative 7. And there you go. I guarantee if you were to multiply this all out and gather together like terms, you would get back your dividend here. All right. So again, this is called the divisor polynomial. This is the quotient polynomial, q of x. And this is the remainder polynomial, r of x. So that's an alternative way to represent your result after performing long polynomial division here. Any questions about this long polynomial division? All right, maybe we can try another one here. Let's see if we can take negative 5 plus x plus 4x squared plus 2x cubed plus 3x to the fourth. And let's see if we can divide this by x squared plus 2. Well, we're going to do so by using long polynomial division. So try now. Put the long division bar down here. Here's my long division bar. Now, notice my divisor is missing a power of x. I got an x squared term, and I go down to a 0th degree term. I'm missing an x to the first power term in between here. Because of that, we need to insert what's called a placeholder in the form of 0x. It's not going to change my divisor. It's just going to hold in a very important place. So you must have a placeholder put in here. So x squared plus 0x plus 2. There's my divisor with the placeholder. Notice my dividend's all out of whack. For one thing, it's not even in descending order. But I do have all powers of x: 4th degree term, 3rd degree term, 2nd degree term, 1st degree term, and 0 degree term. So we do not need any placeholders in our dividend, but I am going to put it in descending order. All right, now we're going to proceed to divide. We're ready to begin our division here. We ask ourselves, how many times is x squared divided into 3x to the 4th? For the first round of division, feel free to take the 3x to the 4th, place it over the x squared, reduce this, and you'll have the first term that belongs in your quotient. 3x to the 4th divided by x squared. When you divide like bases, you subtract exponents. This is going to leave us with 3x squared. So 3x squared is the first term in our quotient, and to keep like terms lined up in columns, I will place it above this 4x squared term here. I'm now going to take 3x squared and multiply it by my divisor. 3x squared times x squared gives me 3x to the fourth. 3x squared multiplied by 0x is going to be 0x cubed. 3x squared times 2 is plus 6x squared. And now we have to subtract off this whole polynomial. 3x to the fourth minus itself goes to 0. Negative 2x cubed subtract 0x cubed is minus 2x cubed. 4x squared subtract 6x squared is minus 2x squared. Bring down the next term as we set ourselves up for round 2 of division. All right, round 2 of division. We ask ourselves, how many times is x squared divided into negative 2x cubed? To answer that question, put the negative 2x cubed over x squared, reduce. And this reduces down to negative 2x. So minus 2x is the next term in our quotient. Take the negative 2x, multiply it by your divisor. Negative 2x times x squared is negative 2x cubed. Negative 2x times 0x is plus 0x. Negative 2x times 2 is minus 4x. Subtract off the whole polynomial. All right. Now, negative 2x cubed minus itself is 0. This goes to 0. This 3's drop out. Negative 2x squared minus 0x squared is minus 2x squared. And 1x, subtract the negative 4x is 1x plus 4x, which is 5x. Drop down to negative 5 as we set ourselves up for round 3 of division. Round 3. We ask ourselves, how many times is x squared divided into negative 2x squared? To answer that question, put the negative 2x squared over x squared and reduce. This reduces down to just negative 2. So minus 2 now is the next term in our quotient. Take negative 2, multiply it by your divisor. Negative 2 times x squared is minus 2x squared. Negative 2 times 0x is 0x. And negative 2 times 2 is minus 4. Subtract off the whole polynomial. Negative 2x squared minus itself is 0x squared. 5x minus 0x is 5x. Negative 5 subtract a negative 4 is really negative 5 plus 4, which is negative 1. We have nothing else to bring down, and so we're done. This is our remainder here. This is your r of x. This is your q of x, your quotient polynomial. And this is our divisor polynomial d of x. And so if you wanted to represent your final answer, you could take your dividend here, which is 3x to the fourth minus 2x cubed plus 4x squared plus x minus 5. You can set that equal to your divisor, which is x squared plus 2 times your quotient being 3x squared minus 2x minus 2, plus your remainder being 5x minus 1. And there you go, ladies and gentlemen. By the division algorithm, we've written our polynomial function f of x as our divisor polynomial times our quotient polynomial plus our remainder polynomial. Any questions how we perform that long division there? Notice we had to put in a placeholder for our divisor. So make sure that both divisor and dividend are written in descending order, and make sure you're not missing any powers of the variable. If you are, you have to put placeholders in. All right. All right, for classwork number 1, now I'm going to have you do this long polynomial division. Today is March 2nd. I want you to take 2x squared plus 3x minus 14 And I would like you to divide this polynomial by x minus 2 using long division. Go ahead and do that, ladies and gentlemen, and we'll check your answers. Okay. So go ahead and perform long polynomial division. All right, when you perform this long polynomial division, your quotient is going to be 2x plus 7. That is your quotient polynomial. Your divisor was x minus 2, and your remainder is 0. Any questions how we did that there? So you could write this as 2x squared plus 3x minus 14 equal to your divisor, which is x minus 2, times your quotient, which is 2x plus 7, and your remainder is 0. And you can clearly see that if you do FOIL this out or multiply this out, you are going to get, you know, what we have here. So makes sense there. Now, there is a quicker way to divide a polynomial by a binomial. As long as your binomial has a certain form, you can utilize this quicker method of division called synthetic division. And synthetic division requires that your binomial divisor be of the form of x minus c, where c is an integer. And what we do then is we take this number c and we divide it into the coefficients of our polynomial function. As long as they are written in descending order. This is called synthetic division. Nice thing about synthetic division is it takes long polynomial division and basically compresses it to one line. And you don't see any variables in synthetic division. All you see are numbers. So it's so much more efficient to divide a polynomial by a binomial divisor that looks like this. So if d of x, our divisor, is x minus c, we divide c into f of x. If our divisor d of x is of the form of x plus c, we divide negative c into f of x. So what I'm going to do is I'm going to rework this problem here, but this time I'm going to divide using synthetic division as opposed to long polynomial division, and we'll convince ourselves that we get the same answer, the same quotient. So here we go. So we're going to divide synthetically. That means I take this 2 here and I divide it into the coefficients of my polynomial f of x. The key is you got to make sure that these are in descending order. If you don't have these in descending order, you're going to have an error. So therefore, 2, 3, and negative 14. Notice I did not have to put any placeholders in my dividend. Synthetic division is very easy to perform. It's actually pretty enjoyable. All you do is you multiply, bring the number up, and add. 2 times 2 is 4. Bring the number up and add. 3 plus 4 is 7. Multiply. 2 times 7 is 14. Bring the number up and add. And you get 0. This 0 is called your remainder. That's your remainder. So what's our quotient? We took a second-degree polynomial and divided out a first-degree binomial. Therefore, when you take a second degree and divide it by a first degree, you're left with a x to the 2 minus 1 power, or you're left with a first-degree quotient. So our quotient is going to be right here, 2x plus 7, and the remainder is 0. That's the same quotient, ladies and gentlemen, that we got when we performed long polynomial division. 2x plus 7. Remainder of 0. So you gotta love synthetic division. It basically compresses this down to 1 or 2 lines. That's it. And notice there's no variables in synthetic division. So synthetic division is a marvelous way to speed up our polynomial divisions. Any questions how I synthetically divided there? Let's try another one.
Is this one also classwork?
No. I'm going to work through this one. So we're going to divide synthetically here. All right, so here we go. Notice my divisor is the proper form of x minus c. So I'm going to divide a positive 4 into the coefficients of this polynomial. But notice we have an issue here because this is not in descending order. So make sure when you put the coefficients in your synthetic division bar for your polynomial that they are in descending order. So here we go. I'm going to divide 4 synthetically into, what would be my leading coefficient here? If this is to be in descending order.
2.
Positive 2. Next coefficient is negative 10. I'm missing an x to the first power term in here. Because of that, I must enter in a placeholder in the form of 0. This is for the x to the first power term. That's a placeholder. And then I got my constants, my constant minus 5. We're ready to begin our synthetic division. Bring down the 2, and here we go. We multiply, bring the number up, and add. 4 times 2 is 8. Add, you get -2. 4 times -2 is -8. Add, you get -8. 4 times -8 is -32. Add, you get -37. And we're done. We have just divided this trinomial by this binomial. This is your remainder. And our quotient polynomial is going to be 2x to what power? I took a 3rd degree and divided out a 1st degree. Therefore, my quotient is of degree 3 minus 1 or 2nd degree. So 2x squared minus 2x minus 8. That's your quotient polynomial. This is your remainder. And we're done. See how quick that is as opposed to long polynomial division?
Do you include the remainder in the answer?
Well, one way to write this is in accordance with that division algorithm I showed you. So to write our final answer, we could say that our polynomial function, which is 2x cubed minus 10x squared minus 5, is equal to our divisor. Our divisor polynomial was x minus 4 times our quotient polynomial, which is this guy right here, 2x squared minus 2x minus 8, plus your remainder, which is to say plus a -37. And there you go.
So which one of those ways will it be on Alex? Because sometimes when you get on Alex, it's a little bit different.
Yeah, I think when you get into Alex, the environment will show you how to enter it in. And here's what you might want to do before you actually, submit your answer. When you get to a problem like this in your homework in Alex, make sure you look at an example and they'll show you precisely how you should enter your answer in. Does that make sense?
Yes, thank you.
That's what you want to do. Yeah, make sure when you get in your homework, you just look at an example first, and they'll show you how your final answer should appear, and then you can work your problem out and represent your final answer the way they represented it in Alex. All right, there you go. And as always, let me know if Alex marks anything wrong that you strongly feel that you have correct, and I will investigate. And if need be necessary, I'll give you the points back, because sometimes Alex is a little bit picky as to how you enter things in. Despite you having done the problem correctly, it might mark it wrong because it just doesn't like your syntactical way of entering it in, which has always been a pet peeve of mine with these online environments. All right, here we go with our first theorem in this section. It's called the remainder theorem. And as always, all theorems are pretty important in mathematics, and they have been proven, and they do have a proof, but we're not going to get into the proof. This is not really a proof writing course here. I'm just going to state the theorem, and we're going to learn, and we're going to try to understand what it's saying. It says, if a polynomial f of x, a polynomial function f of x, is divided by x minus c, then this theorem goes on to guarantee that the remainder, the remainder is going to be equal to the polynomial function f of x evaluated at that number c. That's what the remainder theorem guarantees. Let's look at an example to breathe life into this theorem. Usually you have to look at a good example to have the theorem come into focus in your mind. At least that was myself when I was learning about all these theorems. Suppose I want to take this polynomial function, this 4th degree, and suppose that I want to divide my polynomial function by this divisor, which is x plus 2. And we're going to use synthetic division to do so. Is my divisor a candidate for synthetic division? Yes, it is. X plus 2, because x plus 2 can be rewritten equivalently as x minus a -2. And so what am I going to divide into my coefficients of f of x? Am I going to divide in +2 or -2? What do you think?
-2.
Got to be a -2 in this case. I always remember it this way. It's always the opposite of whatever sign you see here. So if this is a plus, you divide in a negative. If this is a minus, you divide in a positive. All right, now let's put the coefficients in descending order. If we have any placeholders that need to be inserted, we must always be conscious of that. 1 is my leading coefficient. My next coefficient is 4. I am missing a second degree term in X. Because of that, I must enter in a placeholder in the form of 0. That holds the place for the second degree term in X. -2 is the next coefficient, and positive 18 is the constant. We are ready for synthetic division. Multiply, -2 times 1, bring the number up and add. 4 plus a -2 is 2. We always add. -2 times 2 is -4, bring the number up and add. You get -4. Multiply, -2 times -4 is positive 8. Add, and you get 6. -2 times 6 is -12. Bring the number up and add. You get positive 6. This is your remainder, 6. So, ladies and gentlemen, what's the significance of this remainder? Well, we're going to find out. I'm going to take my polynomial function f of x, and I'm going to evaluate it at this number c that I divided in, which is -2. So I'm going to evaluate my function, polynomial function at -2. That means I'm going to put -2 in everywhere we see x. And then I'm going to evaluate this using my order of operations. All right, here we go. We do exponents first. So -2 to the 4th power is a -2 times itself 4 times, which nets us 16. This is -2 to the 3rd power, which is -8, and -8 times 4 is -32. -2 times -2 is +4, and then we have +18. Combining all these numbers, this is -16, +4 is -12, +18 is going to give us 6. What's the significance of this 6? When I evaluated my polynomial function at -2, this 6 is equal to the what? The remainder. You see that there? It's equal to the remainder, because that's not a coincidence. That's what the remainder theorem predicts and guarantees. And when you divide -2 into the coefficients of a polynomial function, it's the remainder that is equal to that polynomial function evaluated at that number c. So do we see how the remainder theorem is working here? So the beautiful thing about the remainder theorem is that if you want to evaluate a nasty polynomial function at some input value, instead of, putting the value in for x everywhere and going through and cranking out the result, synthetic division is more pleasing to do. It's easier to do. So I would probably just use synthetic division to determine that f of -2 is equal to 6 instead of doing it this way. Okay. So that's what the remainder theorem says. And that's not just the only use for the remainder theorem. I mean, because some of you are saying, well, big deal. I mean, I could have just put -2 in here and got this, Why did I have to do that, Well, you'll see the consequence of the remainder theorem and the more important aspect of that it affords us. But does that make sense so far, what the remainder theorem is saying through this example here? Okay. All right, so let's try another one here, maybe taps into this remainder theorem. So that is the remainder theorem. And this next one says this, suppose that I am given a 4th degree polynomial function here. This should be cubed. And this is 12x squared minus 30x plus 35. Suppose that I want to find this function evaluated at -7. The long, kind of hard way of doing this is to put -7 wherever you see x, put -7 in for x everywhere, and then to go through and crank this out, which doesn't seem like much fun at all. Ladies and gentlemen, let's have more fun in doing this. Let's synthetically literally divide -7 into the coefficients of f of x. Notice we don't need any placeholders, 4th degree, 3rd degree, 2nd degree, 1st degree, 0 degree term. And our coefficients are in descending order. Make sure they're always in descending order. All right, here we go. -7 times 1 is -7. Add, you get -1. -7 times -1 is 7. Add, you get -5. -7 times -5 is 35. Add, you get 5. -7 times 5 is -35. Add, you get 0. What is f of -7 equal to? Anybody?
0.
0. It's equal to the remainder by the remainder theorem. You see that there? And you got to admit, synthetic division was a lot quicker than, plugging -7 in here and going through all this. So you got to love that remainder theorem. Furthermore, ladies and gentlemen, the significance of our remainder being 0 has real deep meanings as to what this -7 is really all about. We say, since our remainder r of x is equal to 0, we say that x equals -7 is you ready for this? It's a 0 of f of x. Or is an x-intercept. It's an x-intercept of the graph of f of x. It's an x-intercept. Furthermore, ladies and gentlemen, we're about to learn another theorem right around the bend from there called the factor theorem. And the factor theorem says that since x equals -7 is a 0 of f of x, or is an x-intercept, also we can say that x minus a -7 or x plus 7 is you ready for this? It is a factor. It's a factor of f of x. And that is guaranteed by the next theorem, which I'm about to show you, called the factor theorem. So, pretty interesting here. Because we got a 0 remainder when dividing -7 into the f of x, we can conclude that -7 is a 0 of f of x, or it's a x-intercept of the graph of f of x. And therefore, x minus -7 or x plus 7 is also a factor of f of x. And therefore, that leads me to showing you the next theorem, which formalizes why I can say x plus 7 is a factor of f of x. It's called the factor theorem. This factor theorem is a two-way street theorem. It's an if and only if theorem that basically goes in both directions. Some theorems are one-way street theorems, whereas others are two-way streets. This is a two-way street theorem called the factor theorem. It's in section 3.3 in your textbook. It says, let f of x be a polynomial function. If we evaluate our polynomial function f of x at some number c and we get 0, then, ladies and gentlemen, we can conclude that x equals c is a 0 of f of x. And furthermore, x minus c must be a factor of f of x. That's what the factor theorem guarantees. But this theorem works backwards too. It says that if x minus c is a factor of f of x, then guess what? C must be a 0 of f of x, meaning that f evaluated as c better give you 0. This is called the factor theorem. So that factor theorem helps us to identify factors of a polynomial function, provided the remainder is equal to 0 after synthetically dividing in the number into the polynomial. So we learned two theorems, the remainder theorem and now the factor theorem. Okay. All right. Any questions so far here? We picked up on two theorems now. Remainder theorem.
Can you go back to the theorem for a second? Sorry.
Now the factor theorem.
Yeah.
Is right there.
Thank you.
All right. Let's try this one now. Is 1 plus 2i a 0 of f of x? equal to x cubed plus x plus 10. Now, the tough way of determining this or answering this question is to put 1 plus 2i in for x here and crank it all out. But it sure doesn't look like much fun to cube 1 plus 2i. So ladies and gentlemen, there's an easier way. The easier way is to use synthetic division and the remainder theorem and the factor theorem. So I'm going to synthetically literally divide 1 plus 2i into the coefficients of f of x. Now we're going to need some lateral space here because we got a real part and an imaginary part in this complex number. So make sure you use a little room here. My leading coefficient is 1. I don't have an x squared term, so I must put in a placeholder 0 for x squared. I have a first degree term, its coefficient is 1, and I have a constant term, which is 10. Let's begin our synthetic division. What's 1 plus 2i times 1? Well, 1 plus 2i times 1 is 1 plus 2i. And now we add. 0 plus 1 is 1, so this still gives us 1 plus 2i. Now we're going to have to multiply 1 plus 2i times 1 plus 2i. And so we're going to have to go back in our thinking as to how to multiply some complex numbers together. 1 plus 2i times 1 plus 2i. 1 times 1 is 1. 1 times 2i is 2i. 2i times 1 is another plus 2i. 2i times 2i is 4i squared. Adding our middle terms together, we get 4i. And 4 times I squared is 4 times negative 1, which is negative 4. Hence, putting this in standard form for a complex number, we have negative 3 plus 4i. Let's bring that up and put it right in here. So negative 3 plus 4i. Now we add these together. Now you can only add real parts together and complex parts or imaginary parts together. Don't add real and imaginary parts together. So 1 plus a negative 3 gives us a negative 2 plus the 4i. Finally, one last thing now is we got to multiply 1 plus 2i times negative 2 plus 4i. So I will do that right here. One times negative 2, negative 2. 1 times 4i, 4i. 2i times negative 2 minus 4i. 2i times 4i, 8i squared. What happens to the two middle terms? They're gone. We're left with negative 2, and this is 8 times a negative 1, which is minus 8. What do these add up to? Negative 10. Bring it up, add. What does this give us for a sum? 0. Ladies and gentlemen, you be the judge. Is 1 plus 2i a 0 of f of x? Yes or no?
Yes.
It is. It's a 0 because we got a 0 remainder upon dividing 1 plus 2i into f of x. So yes, the answer is yes, because you could clearly see now that if I evaluated my function at 1 plus 2i, I would get, according to the remainder theorem, I would get 0 for that result. So clearly this is a 0 because any value that sends a function to 0 is a 0. That's why they call them zeros. Okay. So that is a 0. Any questions how I verified that 1 plus 2i is a 0 of f of x there? Okay.
How would you write the answer?
Well, you can basically just say yes. This is the work to this is the work that basically supports your response of yes. Okay.
Well, I mean, if you're writing out the answer with the i's included, though, in general, how would you write the answer?
Well, I guess I'm not understanding what you're asking for. I just want to know if this is a 0 for the f of x. It is a 0, correct? Because we got a 0 remainder here. All right.
Okay.
So if there's questions like that on Alex, it'll just ask.
Oh,
Yeah.
yeah. I mean, yeah, we have a question like this on Alex. Look, again, this is the key thing with Alex. When you're doing homework problems, if you're not 100% sure as to how to enter in the answer, always look at a what and an example first. Okay. I have them walk you through an example and show you how they actually display the final answer, because the way they display it is the way that you will display it. Okay.
Yeah. Well,
Yeah. Always look at an example.
I just meant like if you're ever having to write out like the bottom line, like 1 plus 1 plus 2i minus 2 plus 4i, if we're ever having to write that out as an answer, and like instead of
Well, we will when we start taking a polynomial and we're being asked to completely factor down in the linear factors. Then we're going to have to, utilize these, okay, in the bottom row here. All right, so stay tuned on that issue because we will be seeing it in the near future. All right. So as it turns out, 1 plus 2i is a 0 of this polynomial function. And therefore, by the factor theorem, we could say or conclude also that x minus 1 plus 2i must be a what? That must be a factor of f of x by the factor theorem. That must be a factor because that's a 0. Right? Now, this is not an x-intercept because x-intercepts only appear in the what? Real plane, correct? You're not going to see this as an x-intercept in the xy plane because that's not the complex plane, it's the real plane. But it is a 0 nonetheless of f of x, don't get me wrong. All right, let's see. Is x minus 3 a factor of this polynomial? X to the 4th minus x cubed minus 11x squared plus 11x plus 2. Is x minus 3 a factor of this polynomial? Well, the easiest way to find out is to synthetically divide what into the coefficients. What am I going to divide in? 3 or negative 3? Better be positive 3. And notice we're not missing any powers of x in our polynomial. So in go the coefficients. And here comes synthetic division. 3 times 1 is 3. Add, you get 2. Multiply, add, multiply, add, multiply, and you what? Add. What's my remainder? Negative 10, correct? So, as it turns out, our polynomial f evaluated at 3 is equal to what? 10. It's not equal to 0. So is this a factor? Is x minus 3 a factor? The answer is no, because 3 is not a 0.
Why did you switch the signs?
What's that?
Why did you switch the signs?
Right up here?
Yeah.
Yeah, okay, because in general, when you got x minus c, you always divide in the opposite of whatever sign you see here. So if you see a minus, you got to divide a positive c in. If you had x plus c, you got to divide a negative c in. Okay, negative. It's always the opposite of this sign here. All right.
Gotcha. Thank you.
So that's not a factor, and therefore x equals 3 is not a 0. And it's certainly not an x-intercept of the graph of this polynomial here. Okay, let's see what time we have here.
I have a question.
Yeah.
So when you use the opposite sign, is that only going to be applied for synthetic division, not the long
Yes, this is only for synthetic division because your binomial has to look like one of these guys for synthetic division. Okay. It's not, you don't apply this to what? Long polynomial division. Okay, let's see here. All right, you try one now. I've shown you that problem. Let's call this classwork number 2. And the question is this: is x plus 2 a factor of this polynomial f of x, which is x to the 4th minus x cubed minus 11x squared plus 11x plus 12? So that is the question. Is x plus 2 a factor of this polynomial function? Go ahead and do that. This should not really take too long, in all honesty. Go ahead and answer that question. Yes or no? Is x plus 2 a factor?
So for it to be a factor, the remainder has to equal 0.
That is correct.
Okay.
So what do you think? Ladies and gentlemen, is x plus 2 a factor?
No.
It is not, because we did not get a 0 remainder. So the answer is no. X plus 2 is not a factor, and negative 2 is not a 0 either, because our remainder is not equal to 0. Okay, that's all you got to do. All right. So we understand how we're using synthetic division, the remainder theorem, and factor theorem to do a couple problems here so far. All right. Our ultimate goal is to be able to take a long, huge polynomial and completely factor it down to linear factors and find all the zeros of the polynomial. Something that we would not be able to even think of doing in elementary or intermediate algebra. So we're really advancing our plane of thought here in this course. Suppose I want to factor this polynomial function into nothing but linear factors. But still be in section 3.3, I have to leave a training wheel on still. We will not learn how to take that training wheel off until section 3.4. And the training wheel that I'm going to leave on is I'm going to have to give you one of the zeros of this polynomial so we can have a jump start. So given that x equals -5 is a 0 of f of x. So I'm telling you that -5 is a 0 of f of x. All right, so how's that going to help us? Well, we know that -5 is a 0 because we're being told it's a 0. So therefore, let's synthetically divide -5 into the coefficients of f of x in descending order. And when I get done doing this division, what had I better get for a remainder? What must my remainder be?
0.
It better be 0, or otherwise this is a lie up here. Okay. All right. So here we go. 3, 25, 42, -40. Notice no placeholders are needed. 3rd degree, 2nd degree, 1st degree, 0 degree. Let's do our synthetic division now. -5 times 3 is -15. Add these together, you get 10. -5 times 10 is -50. Add these together, you get -8. -5 times -8 is +40. And we get exactly what we anticipated, namely a 0 for the remainder. It has to be 0 because I indicated that this is a 0 of the polynomial. All right. So where do we go from here? We know that x minus 5 is a 0. So therefore, we also know, ladies and gentlemen, that X what? Plus 5, X minus a negative 5, which is X plus 5 must be a what? A factor of f of X. Isn't that true? If negative 5 is a 0, X minus a negative 5, which is X plus 5 must be a factor of f of X by the factor theorem. Well, when I factor X plus 5 out of this third degree polynomial, what do I leave behind? Well, what I leave behind is going to be given in our last row of our synthetic division down here. What I'm going to leave behind is I'm going to leave behind the polynomial 3x squared plus 10x minus 8. That's what I leave behind. Now, can we factor this using our traditional methods from elementary and or intermediate algebra? We should be able to take this the rest of the way without utilizing synthetic division anymore. How do we factor this difficult trinomial? 3 times a negative 8. Is this even factorable? 3 times negative 8 is negative 24. Do there exist 2 factors of negative 24 that sum up to positive 10? Do they exist?
Six and four.
I think after a little thought, did you say 12 and negative 2?
No, I said 6 and 4.
Oh, 6 and 4 don't work because you'd have to have a negative 6 and a positive 4, which don't add up to 10. Or you'd have to have a positive 6 and a negative 4 that still don't add up to 10. The only ones that work are going to be 12 and negative 2. These sum up to 10 and are factors of negative 24. So this trinomial does factor. I am not going to take the time to factor it. We've already looked at, methods for factoring this type, usually like the grouping method, or if you want the trial and error method, you can use that. The bottom line is that trinomial will factor into the product of these two binomials, namely 3x minus 2 times x plus 4. So we have accomplished something that we would not be able to do in elementary or intermediate algebra, ladies and gentlemen, because notice with the 4-term polynomial, the only thing we would know how to do back in those courses is the grouping method. But grouping does not work here, it fails. The only thing you'd be able to factor out of the first 2 terms would be x squared, and you leave behind 3x plus 25, but that's sure not what you're going to leave behind after you factor something out of these last 2 terms. So the grouping method fails here. And so back in those classes, we would say, well, basically it can't be factored. Well, guess what? We're staring at its complete factorization right here. Now that I have the complete factorization, I should be able to find all the remaining zeros of f of x just by setting f of x equal to 0 and then setting my factors equal to 0. Well, solving this equation, we get x equals negative 5. That's a 0. We've known that. We were told that. What's the multiplicity of this 0? What is the multiplicity? Well, it came from this factor that's raised to the first power. So its multiplicity is 1, meaning it occurs only 1 time as a 0. To get the other zeros of our polynomial, take 3x minus 2 and set it equal to 0. This factor and solve for x, and you discovered x is equal to 2/3. That's another 0 of f of x, also a multiplicity of 1. To get the final 0, take the last factor, set it equal to 0, solve for x, and you get x equals negative 4, also of multiplicity of 1. Not only, ladies and gentlemen, are these zeros of f of x, these are also called what? Graphically, they're called the x-intercepts. Furthermore, from the cross-touch point theorem from yesterday, do you remember, will our graph touch the x-axis at these x-intercepts or cross through the x-axis? What would be the case? Anybody? Does the graph just touch the x-axis at these values, or does it actually cross right through the x-axis? What do you think? Anybody remember the cross-touch point theorem?
I'm pretty sure it crosses.
It would cross right through every one of these, the x-axis at every one of these values, because these are of odd multiplicity. Okay, that was a theorem from yesterday.
How do you figure out the multiplicity one more time?
Well, multiplicity comes from the fact that these factors are all raised to the first power, and that's why we say their multiplicity is 1. Okay, in other words, we don't have any repeated zeros. This one only occurs once. Okay. All multiplicities of 1. Now, if this was x plus 5 to the second power, then negative 5 would be a 0 of multiplicity of 2, meaning it would repeat twice if this was the second power, but it's not. Okay, ladies and gentlemen, we are ready to close the door on 3.3, and let's now move into 3.4. And we have some wonderful theorems awaiting us in this next section that are going to enable us to move closer to our ultimate goal in this chapter. The next theorem we're going to look at in section 3.4, which is entitled Zeros of Polynomials, is called the rational zero theorem. This is the theorem that's in your textbook in section 3.4. And this is what the theorem says. It says if f of x is a polynomial function, an nth degree polynomial function with integer coefficients, that means all these coefficients A have to be integers. They cannot be decimals or they cannot be fractions. They have to be integers. Well, this rational zero theorem says that if this polynomial function, this nth degree polynomial function, has a rational zero is a fractional zero. If it does, then that rational zero must be of the form of P over Q, where P must be the factors of the constant term of your polynomial. Q must be a factor of your leading coefficient of your polynomial. That's what the rational zero theorem guarantees in section 3.4. And as always, I like to show you an example to breathe life into this theorem, because right now it probably means probably a hill of squat at this point in time. Okay, so let me show you an example so that we can further understand what the theorem is really saying. All righty, and again, this theorem is in your textbook for your viewing. Let's look at an example to try to, put this rational zero theorem to work for us in hopes of understanding it better as to what it's really saying. Well, here we go. Suppose that I have a polynomial function f of x, which is a 5th degree polynomial. And suppose, ladies and gentlemen, I want to find all potential. What does the word potential mean? Potential. Rational zeros. I want to try to find all the potential rational zeros of f of x. Well, to the rescue is the rational zero theorem. And the theorem says this. It says that if this 5th degree polynomial has a rational zero, a fractional zero, it may not have any rational zeros. But if it does, the rational zero theorem guarantees that it must be a rational zero of the form of P over Q. Has to be of this form. Where P represents all the factor, where P represents a factor of the constant term, in this case, positive 10. Q represents a factor of the leading coefficient, negative 2. So what are factors of P? What are factors of 10? I like to call this the P list we're about to build here. What are all factors of 10? Positive negative 1 times what? Positive negative 10. Those are factors of 10. Positive negative 2 multiplied by positive negative 5. Those are factors of 10. These are all the factors of positive 10. What are all factors of the leading coefficient negative 2? Well, you could have positive negative 1 times negative positive 2. These are factors of negative 2. So the rational zero theorem guarantees that if f of x has a rational zero, it must be of the form of one of these rational zeros that I am about to list here. So I'm going to simplify this. This is saying that to represent all of our potential rational zeros, we're going to take each number in the numerator and divide it by each number in the denominator. So positive negative 1 divided by positive negative 1 Positive negative 2 over positive negative 1. Positive negative 5 over positive negative 1. Positive negative 10 over positive negative 1. Or we could have positive negative 1 over positive negative 2. Or positive negative 2 over positive negative 2. Or positive negative 5 over positive negative 2. Or positive negative 10 over positive negative 2. Well, some of these are redundant and we need to clean this up. So what are all my potential rational zeros? Well, they're going to be of the form of what's positive negative 1 divided by positive negative 1? How does this simplify? This is just going to simplify down to just positive negative 1. Positive negative 2 is the simplification of this. Positive negative 5, simplification of this. Positive negative 10. Positive negative 1/2. Positive negative 2 over positive negative 2 is positive negative 1, but we've already accounted for that one. Positive negative 5/2. Positive negative 2 divided by positive negative 10 divided by positive negative 2. We've already accounted for that. That's positive negative 5. So there you go. If f of x, if this fifth degree polynomial function has a rational zero, it must be one of these in this list. It has to be in the list here. And how many choices or potential rational zeros are there? Well, how many do we have to choose from? Potentially. Well, I mean, we got, 2, 4, 6, 8, 10, 12 of them. So I have a question for you. If I evaluate my function f of x up here at positive 7, could this ever be equal to 0? F of 7? Why or why not?
No, because it's not in the list of all
That's
the
right.
potential ones.
It's impossible. 7 cannot be a 0 of our function f of x because 7 is not in our list here. The answer is no, can't be. So if f of x has a rational 0, it has to come from this list. That's what the theorem guarantees. It must come from this list. So that's kind of nice. At least this narrows down, if you will. Granted, we still have quite a few choices here, but it still narrows down, the ones we would have to check out to determine which ones actually qualify as being rational zeros. So that's one nice thing about the theorem. It narrows things down a little bit. And Descartes' rule of signs will even narrow this list down even more. Although, unfortunately, I don't think I'm going to have time to get to Descartes' rule of signs. In which case, I think I did make a supplemental video that I'll have to probably put on Canvas for your viewing. It's a rather short video to understand what Descartes' rule of signs can do and how it can narrow this list down, enabling us to more quickly pinpoint any rational zeros this polynomial function may in fact have. Okay. All right. So this is a list of potential rational zeros. The theorem is not saying that all of these are rational zeros of f of x. It's not saying that. It's saying that if the function does have a rational zero, it must come from this list. That's what the theorem is saying. So do we understand what that theorem is guaranteeing now more clearly? The rational zero theorem. Okay, time check. 2. All right, here we go, ladies and gentlemen. We're going to try this one now. Suppose that I want to find all the zeros of this polynomial function. And to make matters more challenging, I'm going to take off the training wheel that we used in 3.3. That training wheel has been removed. We're on our own now. I want to try to identify all the zeros of this fourth degree polynomial function. Furthermore, I want to completely factor it down into linear factors. So I'm going to even take it even further. I'm going to completely factor f of x down. Now I have a question for you. Picture yourself being back in elementary or intermediate algebra, and you're being asked to do this. I have a question for you, ladies and gentlemen. Would we, with our understanding of elementary or intermediate algebra, would we have enough arsenal to take care of this problem back in those courses? There would be no way to do this problem back in elementary or intermediate algebra. We have nothing in our arsenal from elementary or intermediate algebra that can factor down a 5-term polynomial. We don't have anything. We do have the method of grouping, but that works on 4-term polynomials. This is not a 4-termer, it's a 5-termer. So we're out of luck. Elementary and intermediate algebra fall flat on their face in dealing with a problem like this. But this, ladies and gentlemen, is college algebra. And this puts us above the folks that are down there in elementary and intermediate algebra. We're now going to have more doors open up to us, more opportunities to answer questions like this that we could only dream of answering back in those courses. Okay, we're going to show you how to walk through this. First, we're going to have to employ the rational zero theorem to kick this off. And the rational zero theorem is going to give us an idea as to what potential rational zeros we should maybe consider for this polynomial function. They must be of the form of P over Q, where P has to be what? You know how I remember where P and Q go? In the alphabet, P precedes Q, but I remember it's just a reverse for this situation. P comes after Q, just the opposite of the alphabet. That's how I always remember this. P must always be factors of the constant term. Q must always be factors of the leading coefficient. So what are factors of -6? Well, that'll be positive -1 times negative positive 6, or positive -2 multiplied by negative positive 3. Those are factors of -6. Q, what are all factors of positive 2? The leading coefficient, that's going to be positive -1 times positive -2. And now, ladies and gentlemen, we can simplify this list. Notice I would have to place each of these in the numerator over positive -1. But if I do that, that's basically just going to duplicate what we're looking at in the numerator. So here's some potential rational zeros. Positive -1 over this is going to be positive -1. Positive -2 over this is positive -2. Positive -3 over this is positive -3. Positive -6 over this is positive -6. But we have some other potentials. Positive -1/2 could be rational zeros. Positive -2 over positive -2 is positive -1. We already got it. Positive -3/2. Positive -6 over positive -2 reduces down to positive -3. We already accounted for that. Here we go. This is our list of potential rational zeros for f of x up here. Notice we have 2, 4, 6, 8, 10, 12 choices here. Okay, that seems like a lot of choices, but I'll tell you one thing. At least the rational zero theorem has narrowed it down. Without the rational zero theorem, there would be an infinite number of what? Infinite number of rational choices. Infinite number. We'd be here all day. But at least we know where to start, which ones to kind of look at. And here's my advice to you. Always try the easy ones first. Don't do the fractions until the very end if need be necessary. Always try 1 or -2 first because they're the easiest ones to work with. So here's my synthetic division bar. To crack the ice, we're trying to find which one of these divides synthetically into this to giving us a 0 remainder. A 0 remainder. Well, my coefficients in descending order are going to be 2, 5, -2, -11, and -6. Here's another thing that's going to be a big help if you can remember this. Let's say we want to try 1 first, positive 1. Well, let's say we go through with 1 and we don't get our 0 remainder. That means we what? Cluttered up our paper for no reason. Okay? So, ladies and gentlemen, you can try 1. But if you don't have something you can erase, then you might be making a mistake because 1 may not pan out. So here's something else that you can do. You can do this in your mind visually and see if it works. And if it does, then we'll pencil in the details. For instance, it's not too difficult to do this mentally. 1 times 2 is what? 2. You bring a 2 up here. What's 5 plus 2? That'll be a 7 here. What's 1 times 7? 7. 7 plus a negative 2 is a 5. What's 5 times 1? 5. What's negative 11 plus 5? Negative 6. 1 times negative 6 is negative 6, but these would add up to negative 12. 1 does not work. Try negative 1. Negative 1's in our list. Let's do it visually first, and then if it works, we'll pencil in the details. What's negative 1 times 2? That gives me negative 2. What's 5 plus a negative 2? 3. What's negative 1 times 3? Negative 3. What's negative 2 plus a negative 3? Negative 5. What's negative 1 times negative 5? 5. What's a negative 11 plus 5? Negative 6. What's negative 1 times negative 6? 6. Oh, and these add up to 0. We found one. Negative 1 is a 0. Let's pencil in the details. Negative 1 times 2 is negative 2. Add. Negative 1 times 3 is negative 3. Add. Negative 1 times negative 5 is 5. Add. Negative 1 times negative 6 is 6. Add. 0 remainder. We have found a 0 of f of x. It's negative 1. We cracked the ice. Okay. Now that we found a 0 for f of x, we know that x minus a negative 1 or x plus 1 is a factor of f of x. Sometimes these zeros in this list can be repeated zeros. They might have a multiplicity more than 1. So sometimes, ladies and gentlemen, you might want to try to see if it works again. We can use what's called repeated synthetic division. We can pick up where we left off here. Let's try negative 1 again. But before I push the writing instrument, I'm going to do this again visually, mentally in my mind. Negative 1 times 2 is negative 2. 3 plus a negative 2 is 1. Negative 1 times 1 is negative 1. Negative 1 plus a negative 5 is a negative 6. Negative 1 times negative 6 is a positive 6, and we get another 0 remainder. It looks like 0 is a repeated 0. Excuse me, it looks like negative 1's a repeated 0. Negative 1 times 2 is negative 1. Add. Multiply. Add. Wait a minute here. This should be negative 2. Add, and you get what? This should be a 1. 1. It wouldn't hurt to have some white out handy too. Negative 1 times 1 is negative 1. This should be negative 1. This will be a negative 6. Negative 1 times negative 6 is 6, and we get another 0 remainder. That means that negative 1 is a 0, okay, that repeats not once, but twice. All right. So how many divisions have I done here so far? How many divisions have I done? I performed how many divisions?
2.
2. So that means that my 4th degree polynomial I started with, its degree has been knocked down by 2 down to a 2nd degree polynomial. So by the time I get down here, what I have left, ladies and gentlemen, is a 2nd degree polynomial remaining. 2x squared plus 1x minus 6. That's what's remaining. After I factored out x plus 1, how many times did I factor x plus 1 out? Not once, but twice. Wow. We're accomplishing a lot here because we're really starting to tear f of x all the way down into its linear factors. And we're also discovering zeros in the process. Now, you could use repeated synthetic division on what you leave behind here, but you don't need to. You can bail out of it now because we know how to factor this by using elementary methods from our earlier careers in algebra. So we could take this the rest of the way just by factoring this as a normal trinomial now. So therefore, this trinomial, I think, factors 2 times negative 6 is negative 12, and negative 12 factors that add up to 1 would be negative 4 and positive 3. So this does factor. And after working that all out off to the side of your paper using the grouping method or the trial and error method, we will discover that this does factor into what? It factors into this right here, I believe, correct? That would be the factorization of this trinomial here. Ladies and gentlemen, we've accomplished our goal. I've completely factored f of x down into the product of nothing but linear factors. Furthermore, I can identify all the zeros. We know what zeros have we already found so far? This one and this one, which is -1 and -1. -1 repeats twice. So -1 is a zero with what multiplicity? A multiplicity of 2. It's a repeated zero. What's another zero? That comes from this factor being set equal to 0. And solving for x, we get +3/2. This is a zero of multiplicity of 1. This factor set equal to 0. When you solve the equation, gets us another zero as being -2. And it also occurs with multiplicity of 1. Why is -1 of multiplicity of 2? Because x plus 1 is raised to the second power here. All right. Isn't that amazing? We just did something that you could not even think of doing back in elementary or intermediate algebra. Impossible back in those courses. We've taken a 5-term polynomial, and not only did we tear it down and factor it down into nothing but linear factors, but we've also discovered all of the zeros and all of the x-intercepts, because these are also x-intercepts. And can somebody tell me, would my graph of f of x cross through the x-axis at -1 or just touch the x-axis at -1? What would be the case here?
Just touch it.
It would just touch the x-axis at -1, but not cross through, because that's an even multiplicity. The graph of f of x would actually cross through the x-axis at 1.5, because this is an odd multiplicity, and the graph would actually cross through the x-axis at -2, because that's odd multiplicity. Furthermore, if we use the left and right behavior theorem, remember that theorem? Even degree polynomial, leading coefficient that's positive, that would predict that the left behavior of the graph is up and the right behavior is up. You agree? I think that would be more than enough information, knowing all these zeros and x-intercepts, knowing the left and right behavior, to sketch the graph of that 4th degree polynomial function if we wanted to do that. So all the theorems of yesterday are coming back to support us in further analyzing polynomial functions, literally putting them under the microscope. Okay. Did that problem make sense there? 155. Okay. Amazing thing we just accomplished that could not be done in earlier algebra. We've come a long ways now. All right. Some of you are probably wondering, what's the big deal about these zeros of these polynomials? Where can they be used in the real world? Well, ladies and gentlemen, there's a lot of functions in industry that are modeled according to polynomial functions. Many, many different processes out there lend themselves to being modeled according to some sort of a polynomial function. And finding the zeros of such a polynomial function have a lot of deep, important ramifications or interpretations in the context of the application situation. So finding zeros of a polynomial, believe you me, does have applications in the real world and have meaning, okay? They do have meaning, and that's why we focus our attention in finding zeros of polynomials, because a lot of, like I said, natural processes out in the real world are modeled according to polynomial functions. Not all of them, but many are, okay? And that's why we like to really study these polynomial functions here. If we're going to apply them to maybe cost functions or profit functions or revenue functions, or maybe a minimization or maximization problem out there. All right, let's try another one here. Find all zeros of f of x equal to x to the 4th power minus 2x squared minus 3. So we're going to try to find all the zeros of this one. This is a 4th degree polynomial. It only has 3 terms. Rational zero theorem to get us started. What are the potential rational zeros? Well, we're going to list them. They must be on the form of P over Q, where P is a factor of the constant term, Q is a factor of the leading coefficient. So what are factors of -3? That's positive negative 1 times negative positive 3. What are factors of positive 1? Positive or negative 1 times itself, correct? This list is small. The only potential rational zeros for this fourth degree polynomial are going to be just positive negative 1 and positive negative 3. That's it. We only have 4 of these to check out. So let's check them out. Let's try the easy one first. Let's try 1. Always try 1 or negative 1 first. Always. They're the easiest ones to work with. Let's try positive 1. Oh, notice we're missing a third degree term in here. Because of that, I must have a placeholder in between my fourth and second degree term in the form of 0. And we're missing a first degree term in between my second degree term and 0 degree term. You must have another placeholder in here. Those placeholders are very important. Don't underestimate their importance. Looks like they don't contribute to anything, but they do. They're very important. Otherwise, things are not going to work out. All right, 1 times 1 is 1. Bring it up. Add. 1 times 1 is 1. Bring it up. Add. 1 times negative 1 is negative 1. Bring it up. Add. 1 times negative 1 is negative 1. Bring it up. Add. No good, because we did not get a 0 remainder. So 1 is not a 0. Let's try negative 1. Negative 1 times 1 is negative 1. Bring it up. Add. Negative 1 times negative 1 is 1. Bring it up. Add. Multiply. Negative 1 times negative 1 is 1. Bring it up. Add. Negative 1 times 1 is negative 1. Bring it up and add. No good. We did not get a 0 remainder. Negative 1 is not a 0 of this polynomial function. Try 3. Three times 1 is 3. Bring it up. Add. 3 times 3 is 9. Add. 3 times 7 is 21. Add. This don't look good at all. Nah. Remainder of 60. Are you serious? That's not 0. 3 is not a 0. Try negative 3. We're down to our last one. We're down to our last rational potential 0. If this don't work, then we would say that this function has no rational zeros. It's possible. The rational zero theorem doesn't say that your function is going to have a rational 0. All it says that if it does, it has to come from this list. That's all it's saying. That's all it's saying. Negative 3 times this is negative 3. Add. Negative 3. Multiply. Bring up. Add. Negative 21. This is going to be positive 63. No good. No 0 remainder. So, ladies and gentlemen, as it turns out, this fourth degree polynomial function does not have any rational zeros. There's none. None. No rational zeros. So what kind of zeros does this thing have? Well, if it doesn't have rational zeros, it's got to either be irrational zeros, where you have a square root present, or it has to be a non-real 0, where you have I present. It's got to be one of those two. And or both those. Okay. Well, how are we going to find them? The rational 0 theorem fails. What are we going to do? Looks like we're up a creek or a creek. Well, ladies and gentlemen, let's just analyze this function a little bit more. So notice this polynomial function is quadratic in form because the leading degree is 2 times the middle degree. If such a trinomial is factorable, it therefore will always factor into the product of 2 binomials. Therefore, since we have a leading coefficient of 1, let's just try our elementary methods we learned way back. Can you give me a couple of factors of negative 3 that sum up to the middle coefficient of negative 2? Do they exist? They do exist.
Negative 3 and 1.
Negative 3 and 1. This thing's factorable. And it factors immediately into not just x, but x squared minus 3 times x squared plus 1. There, we just factored it. Now to find the zeros, we set y, which is really f of x, equal to 0, which means we have to set both factors equal to 0 and solve each equation to get the zeros. Solving this equation, this quadratic equation, I'll use the square root method. Add 3 to both sides. Take the square root of both sides. Don't forget the plus or minus square root of the right side. and we have two zeros. Ah, no wonder. These are not rational, ladies and gentlemen. These are irrational zeros. These are irrational numbers. No wonder we couldn't find any in here. These are irrational. Oh, wait, we still got some other ones to find. Take x squared plus 1, set it equal to 0, and then solve for x. Which after we subtract 1 from both sides, we get x squared equals -1. Now we take the square root of both sides. This makes sense now. No wonder there's no rational zeros. Because these are irrational zeros, and these are what kind of zeros? What kind of zeros are these? These are imaginary zeros. Imaginary numbers. No wonder we couldn't find them in our list of rational zeros, because there are none. There's none because we discovered these are the zeros of f of x, and they're certainly not rational. They're not rational numbers. This is an irrational number. Its decimal neither terminates or repeats. These are not rational because they're not even real. They're imaginary. Okay. So does that make sense why none of these panned out in this list? None of them worked? Makes sense now. Okay. All right. Wanted to show you one like that. You might run into one like that, and you're wondering what the heck's going on here. All right. There is another powerful theorem in this section, which is really a culmination of all the theorems up to this point. It is called the fundamental theorem of algebra. The fundamental theorem of algebra. That sounds pretty profound and robust in a sense. Basically, the fundamental theorem of algebra says this. It says the number of zeros of an nth degree polynomial function f of x, as long as the degree is at least 1, must be exactly n zeros if counted by their multiplicities. So what's this theorem saying, this fundamental theorem of algebra? Well, I'll tell you exactly what it's saying. What was the degree of this polynomial here? This is a 4th degree polynomial. Do you agree? According to the fundamental theorem of algebra, therefore, that theorem would guarantee that this 4th degree polynomial must have 4 zeros. Or it's guaranteeing that the multiplicities of all the zeros must add up to 4. Well, ladies and gentlemen, we certainly see that we have 4 zeros here. One zero is positive square root of 3, the other one's negative square root of 3. Another zero is positive I, and the other one's negative I. That's not just a coincidence that we have 4 zeros here. That must be the case in accordance with that fundamental theorem of algebra. 4th degree polynomial must have 4 zeros. Was that true with our other examples? Was that true with our other examples? Hey, didn't I just work out a problem? Well, what happened to the paper there? Oh, hold on a second. Remember this problem we just worked out? This is a 4th degree polynomial. We wanted to find all of its zeros. According to the fundamental theorem of algebra, there must be 4 of them, or at least the multiplicities better sum up to 4. What do we get for the zeros? Oh, here they are. If you add these multiplicities together, 2 plus 1 plus 1 is 4. 4 zeros for a 4th degree polynomial function. That's what the fundamental theorem of algebra guarantees. That's why we have 4 zeros, one of which repeats twice. Okay.
Can you go back?
What's that?
Can you go back to the theorem?
Okay, the theorem. The fundamental theorem of algebra is right there. Okay. So if I wanted to find the zeros of a 10th degree polynomial function, how many zeros must it have? A 10th degree. It better have 10 zeros. If I had a 7th degree polynomial, how many zeros must it have?
7.
7 zeros. So when you find the zeros of an nth degree polynomial, you better get n zeros in the end. Or another way to say that is the multiplicities of all the zeros better sum up to n, okay? Because you could have some repeated zeros. Or zero, yeah, you could have repeated zeros. Now, is this fundamental theorem of algebra saying that all of my zeros will be rational zeros? It's not saying that. Is this theorem saying that all my zeros will be irrational zeros? It's not saying that. Is this saying that all my zeros will be complex or imaginary zeros? It's not saying that. All it's saying is that if we have an nth degree polynomial, the sum of all the multiplicities of all the zeros better add up to n. In other words, essentially, you better get n zeros for an nth degree polynomial. That is always a guarantee by this theorem. Furthermore, ladies and gentlemen, how about those complex zeros? How about if you have imaginary zeros for a polynomial function, f of x? Well, here's another little powerful, useful theorem. It's called the conjugate pair theorem. This conjugate pair theorem says that if we have a polynomial function f of x, and a plus bi is a zero of f of x, then this theorem guarantees that another zero has to automatically be the conjugate a minus bi. Has to be the case. So this is a very interesting theorem because it's saying that complex zeros or imaginary zeros always come in conjugate pairs. They always come in conjugate pairs for a polynomial function. That's pretty amazing. That's important to know that theorem, the conjugate pair theorem. So in other words, if 3 plus 2i is a zero, what's automatically another zero of a polynomial function? Guaranteed. 3 minus 2i also has to be a zero. If 5i is a zero, automatically, what has to be another zero? Guaranteed. Negative 5i must also be a zero. That's what the conjugate pair theorem is saying. So listen to this true-false question very carefully. Can an nth degree polynomial function have, no, listen to this, and you answer true or false. An nth degree polynomial function can have an odd number of complex or imaginary zeros. Is that possible? True or false?
False.
That's false. Because imaginary zeros or complex zeros always come in conjugate pairs, according to this theorem.
Can you scroll down a little bit?
Well, like that's about where I can go there. But so that's an important theorem, knowing that conjugate pair theorem, because I'll tell you why it's important. Because if I give you a complex 0 to f of x, then automatically you know another one. It must be the complex conjugate. It has to be. That's why it's important. All these theorems are very important. They're going to help us very efficiently assess the zeros and the factorization of huge polynomials, no matter how big they are. These theorems all go to bat for us and enable us to eventually tear the thing all the way down into linear factors and find all of the zeros too. Even if those zeros, some of them are not real, it'll still enable us to find all the zeros. So we really come a long ways in this session here. We've learned a lot. We've amassed or taken on some theorems that enable us to do things, like I said, that we could only dream of doing back in elementary or in intermediate algebra. Okay? And that's why they call this college algebra, because it's more sophisticated. All right, time check. 2:12. Okay. Ladies and gentlemen, are you ready for a problem here? Your last classwork? Challenging problem, but I would like you to try to do something with this. Okay. Here it is. We'll call it the last classwork here. Given f of x equals x to the fourth minus 6x cubed plus 28x squared minus 18x plus 75. And if I tell you that x equals 3 minus 4i is a zero of f of x, I want you to find all the remaining zeros. So I have a question for you. How many more zeros do we have to find? If I give you one of them, how many more do we got to find according to the fundamental theorem of algebra?
3.
3 more. But wait a minute. Oh, finding the second one should be trivial. What is another zero? Automatically by the conjugate pair theorem.
3x plus 4i.
Well, three what? 3 plus 4i is automatically another 0. So all you got to do is just find 2 more, and we got it. Go ahead and see if you can find those 2 other zeros. I'll give you a hint. How to get started, you're wondering? Synthetically divide this into the coefficients of this polynomial to kick this off. That's how you begin. See if you can walk down the path now to find all the zeros of this thing. And ultimately, we'll be able to factor it into linear factors too once we find the zeros. Go ahead, have some fun. All right, let's take a look here. Well, 3 minus 4i, I told you, is a 0. And you can see that when you synthetically divide 3 minus 4i into the coefficients of f of x, you do get a 0 remainder, as you should. But automatically by the conjugate pair theorem, 3 plus 4i, the complex conjugate of 3 minus 4i, must also be a 0. So I did repeated synthetic division. I picked up where I left off, and I divided 3 plus 4i into what remains. And when I do that, lo and behold, I do get a 0 remainder again, because this is also a 0. Now, ladies and gentlemen, I've done 2 divisions. And so now we got our 4th degree polynomial knocked down to a 2nd degree. And what remains will give us what remains after doing the 2 divisions. We're left with 1x squared plus 0x plus 3 times these linear factors according to the factor theorem. If 3 minus 4i is a 0, x minus 3 minus 4i must be a factor. And if 3 plus 4i is a 0, x minus 3 plus 4i must be a factor. By the way, x squared plus 0x plus 3 is really x squared plus 3. So to find my 2 remaining zeros, I take this factor x squared plus 3 and set it equal to 0, and then solve for x. Using the square root method to solve this quadratic equation, I subtract 3 from both sides, take the square root of both sides. Don't forget the positive and negative square root of the right side. And I get my other 2 zeros as being positive or negative I times the square root of 3. I have found all my zeros. All my zeros would be 3 plus or minus 4i and plus or minus I squared root of 3. Those are all your zeros. Notice a 4th degree polynomial, 4 zeros. Notice all my complex or imaginary zeros come in conjugates, conjugate pairs, as predicted by the conjugate pair theorem. Furthermore, I can further factor f of x down into nothing but linear factors. X minus I squared root of 3 times x minus a negative I squared root of 3, which is x plus I squared root of 3, times these 2 linear factors, which were shown above. So not only do we find all the zeros, we have completely factored f of x down into nothing but linear factors. If you're to take the time and multiply and expand all this out, and to gather together your like terms, you would discover that you would get back your 4th degree polynomial function. And that would be a good thing if you want to challenge. Multiply all that back out. That'll be a very good challenge exercise if you have some extra time. Multiply all this back out. Convince yourself you do get this back, because you must get that back. Did anybody get that?
Yeah.
Well, congratulations. We've come a long ways since 12:30 this afternoon. We have really armed ourselves with a lot of very sophisticated theorems, and they enable us to do things, like I said, that we could only hope of doing back in the elementary courses. All right, so ladies and gentlemen, that's all I have time for. The Carty's rule of signs, which helped narrow down your P over Q list. I will see if I have a video available for that. I'll post it on Canvas and let you know. Just remember, if you haven't completed the exam on chapter 2, to get it done by midnight tonight. And just make sure you do the homework and the quiz first, and also look at the review or preview before you attempt the exam. With that, I'll let you go. Have a great weekend, and I'll stay on the line if you have any other questions.
Yeah, I have some questions.
All right, go ahead.
So we'd been emailing, but for that quiz, I was taking it last night and it had closed at like 10:59, something like that. So I only got, I didn't get very
Which
far
quiz
through
was
it
that? Was
before
that the
yeah.
Alex quiz?
Correct, it was the Alex quiz.
You said it closed down at 10:59?
It did, yeah. So I had just gotten into it, and so it had cut me off, and I think I got like a 22%, something like
That
that.
should have been open till midnight. Okay, what's your last name?
Lyndhurst.
Okay, Lyndhurst. And that was the chapter 2 Alex quiz?
Yeah, the one that was due like
Okay.
Tuesday, but we'd emailed.
Okay. All right. Well, I'll open
And
that
I don't
back
know
up.
if the homework is closed off as well, but that also said it was due at 10:59. So I assumed it was closed off.
All right. So what do you need? You need a quiz and a homework open up, or what?
Yes, I need the quiz and all of the homework opened.
For chapter 2, correct?
Correct, the
Alright,
chapter that we
well,
were
let me-
just
let me
completing.
think here. So what was the deal on that? I gave you an extension because,
My friend had committed suicide.
yeah, okay. All right. Sorry to hear about your friend. How awful.
Yes, and the funeral is Tuesday, so I will not be in class that day.
Okay, I will open that up, okay, I'll open all that up for you, okay? All right,
Thank
I'll
you.
open that up for you and, I don't know, I mean, probably give you through, maybe midnight Sunday night. Do you think you might be able to get it done by then or not?
Yeah, I should be able to get it done by then.
All
And
right,
the exam's still until Friday, correct?
yeah, you think you're gonna be able to do that or?
Yeah, I can probably do the
Okay.
exam before.
All right, I'll take care of that.
All right, thank you.
Yep,
Did you find my email about my attendance that I told you about in last class?
yes, who is this now?
It's Kaylee Green.
Green?
Yeah.
Okay, as far as your attendance is concerned, hold on a second.
Yeah,
Um,
That was